lecture 17, design of slabs, part 4. So, we have come to the part 4 of design of slabs, and let us do one problem on say simply supported case, and other one we shall solve according to say table 26, that is your continuous one. So, here we shall solve example. Let us state the problem first. Simply supported two-way slab with UDL. Please note uniformly distributed load we are talking. So, what we have to do, let us write down in a very explicit manner. Design reinforced concrete slab. The dimension is 5.5 meter into 4.0 meter, simply supported on all the four sides it has to carry a characteristic load, let us say live load of 8 kilonewton per square meter. Concrete M25 and steel Fe415. Exposure condition to environment is mild. So, this is your that problem. So, 5.5 meter by 4 meter. So, obviously, this is a case of two-way design of two-way slab problem. It is supported on all four sides. It has to carry a characteristic live load, not the factored one, that means you have to multiply with 1.5, that is quite high, that is 8 kilonewton per square meter. Concrete M25 and steel Fe415. Exposure condition to environment is mild, because this one will give you to choose or assume the cover, because you are having different cover for different exposure condition. So, in this case we shall take it as a 15 millimeter, and we shall provide that bar less than equal to 12 millimeter dia bar. So, we can use a 15 millimeter that you say cover. Okay. So, number 1, thickness of slab. So, in our case, let us assume that 4.0 meter center to center, and that is our effective span also. In our case, we shall consider, because there is no such support condition or anything, nothing is mentioned. So, we shall assume in this case that is 4 meter is your say effective span, because if it is mentioned that your what is the support, that your say width of the masonry or the support, then we have to calculate your say that effective span. But here in this case we shall take it as a 4 meter, and cover to mild exposure equal to 15 millimeter. Now, we can find out in clause 24.1 of IS 456, there is a note where it states that for simply supported case, that this is for span by overall depth. Please note that overall depth, it is written as overall depth. Simply supported case, it is 35, continuous it is 40. It further mentions, let me write down here, for high strength deformed bar, that is, say here Fe 415, sorry, Fe 415, the above values, let me write down explicitly, should be multiplied by 0.8, just to mention. For high strength deformed bar, as for example Fe 415 in our case, the above value should be multiplied by 0.8. So, span by overall depth we can get it, and we can find out, and we can take it, say, so what we can do it here, we can find out the corresponding value, and which is coming as 0.8. I think I should check it once more. So, page number 39, yes, and it further states, there are few things, it further states that for 2A slabs of shorter spans up to 3.5 meter with mild steel reinforcement, the span to overall depth ratios given below may generally be assumed to satisfy vertical deflection limits for loading class up to 3 kilonewton per square meter, loading class up to 3 kilonewton per square meter. But here, and for that simply supported slabs, that is your 35 and continuous slabs 40. For high strength deformed bars of grade Fe 415, the values given above should be multiplied by 0.8. So, this is your clause, but here in our problem, let us see our problem. Please note, it is told that for mild steel, and that is your, say, 3.5 meter up to 3.5 meter, but in our case it is more than that. That is number 1 violation. Number 2, it is not 3 kilonewton per square meter, it is 8 kilonewton per square meter in our case. That means we little bit violate that rule. So, here what I should say here, that means the this one, sometimes the span by depth ratio, sometimes it may mislead to you, it may mislead you. So, that is why even then we take it as a, say, first assumption. So, in our case, let us take it, say, we shall assume, though it is given 35, let us take span by depth, let us say overall depth itself. Let us take, I shall take it, say, 30, and further I shall modify with 0.8, say, we shall multiply with the 0.8. So, the span by overall depth for this problem, we shall take it, say, 30 into, say, 0.8, say 24. If I am taking this one span by overall depth, that one say I am taking 30, because that one in our case a mile steel. Why I am taking that one for the time being, because there is a, it is not exactly matching with say your that mile steel, because in our case the clause says it is for mile steel up to 3.5 meter, and also the loading, that one will be more than say it will be not be say 3 kilonewton, 3.5 possibly, sorry, 3 kilonewton per square meter. So 3 kilonewton per square meter and 3.5 meter. In our case I do not know, in our case I do not know whether this value will help me, that is why I am going say 30. So otherwise what I can do, let us try problem here, because in this problem let us try first, let us see, maybe it is not economic, but at least it will be safe. That is our guideline, that is our first attempt. When you are doing this problem say first time, so what we shall do, let us keep it in a say safer side, and that is why I am taking 30. So at least I know that it will be in the safer side. But if I take 35, 35 times 0.8 if I take, so 35 times 0.8 let us take, which comes as 28. So I do not know whether at the end, after providing the percentage of steel, I do not know whether it will be safe or not. It is not the case of only for the bending, but we have to check it from the control of deflection point of view also, and that is the span by depth ratio only will help us to that keep it to make us in within the what is called within that control of deflection. That is a span by 350 or span by 250, that is the guideline for the overall deflection. So it should only with this I can keep it within that limit. So here I am taking this 24, that one, and it will be maybe safer side. So I can write down here L by D equal to 24. So D equal to L by 24, and L equal to here 4000, that is in the shorter direction, divided by 24, which comes as so 166.66, let us take 166 millimeter. So what we can do it here, let us provide D equal to 175. This is quite high. This is quite high. Generally in this type of slab, from our experience you will find out it is very, it should be 150 may be sufficient. But anyway, let us take for the first problem, let us take D equal to 175 millimeter. So D provided (175 millimeter). So D should be equal to 175 minus clear cover 15 for mild exposure, minus 10 by 2, which comes as 155 millimeter. Okay. Number 2, here we shall take it as design load. One is the dead load. It can have so many components, say slab 0.175 into 25 into 1 meter width, which comes as 4.375 kilonewton per meter. Let us write down for meter width we are talking. So I can write down a square. Floor finish, let us take floor finish of say 25 millimeter. Let us take floor finish 25 mm thick. So I am taking 0.025 into 24 into 1, which comes as 0.6. Number plaster. Let us take 6 mm thick, which comes as 0.006 times 24 times 1 equal to 0.144 kilonewton per square meter, which comes as 5.119 kilonewton per square meter. What is the live load? So 5.119 kilonewton per square meter is the dead load. Live load, number 2, live load equal to 8 kilonewton per square meter. Therefore, the design load, or factored load, equal to 1.5 times dead load plus live load equals 1.5 times 5.119 plus 8 equals 19.6785 kilonewton per square meter. Okay. Now we have to find out the for this load we have to find out the moment. Maximum factored moment. LY by LX equals 5.5 by 4.0 equals 1.375. Let us take it from table 27 IS 456 2000 LY by LX for 1.3, it is coming between 1.3 and 1.4. So, alpha x, which is given as 0.093, 0.099, alpha y 0.055, 0.051. So, I am taking that interval only 1.3, 1.4 because it is between 1.375. So, we can calculate that alpha x and alpha y from these values we can find out. So, let us calculate that. For Ly by Lx equal to 1.375, alpha x equal to 0.093 plus 0.099 minus 0.093 divided by 0.1 times 1.375 minus 1.3 equals 0.0975. So, we are getting something like this. This is the slope. Alpha y equal to 0.055, 0.055, it comes like this. This is 0.055, here somewhere we are getting 0.051. So, 0.055 minus 0.055 minus 0.051 divided by 0.1 times 1.375 minus 1. Is it so 3? So, we can get, and that value we are getting as 0.052. So, alpha x and alpha y, alpha x and alpha y we can get, and those values we shall use it in our calculation. So, what is the value of then mx? Mx equal to alpha x w L square x equals 0.0975 times 19.6785 times 4 square equals 30.69846 kilonewton meter. My equal to alpha y w again L square x equals 0.052 times 19.6785 times 4.0 square equals 16.372512 kilonewton meter. So, we can get mx and my. Let us check depth. So, 0.69846 kilometer and this one. So obviously we have to check with this value. So let us check depth. So M max equal to 0.138 FCK BD square, D equal to M max by 0.138 FCK B equals, so M maximum out of these two, just let me show you. So out of these two, this is 30.69846 is the maximum. So we shall use this one for checking depth. Here then automatically this one also will be checked. So 30.69846 into 10 to the power 6 divided by 0.138 FCK M25. So 25 times B is 1000 in this case, which comes as 94.329 and less than 155 millimeter, the depth which we have provided. So 155 millimeter is the effective depth provided and we are getting 94.329, that means it is safe. So what about the area of steel then? We can now calculate area of steel. We shall use this formula nowadays. We shall use it now on 1.2 minus root over 1.2 whole square minus 6.6 mu divided by FCK B D square. If we know D, B, everything, so we can find out x by D. What is the value of this portion? We can find out separately. 6.6 mu by FCK B D square equal to 6.6 multiplied by 30.69846 times 10 to the power 6 in Newton millimeter divided by 25,000 is the width, that per meter width, times 155 whole square, which comes as 0.3373316. So x by D equal to 1.2 minus root over 1.44 minus 0.3373316 equals 1.2 minus 1.05. So x by D equal to 0.15 less than 0.48 for AP415. So we can get x by D 0.15 less than 0.48, that we have to check. So we know x by D, so we can now calculate the lever arm. So the thing is that first thing whatever you are doing here, the first thing that you check or you can provide on the basis of that also. Is not necessarily that we have already provided, but it may happen that if you know the moment, so from there you can find out the D 94.329, from here itself you can provide the overall depth. If we forget that span by depth, because after all later on we have to check it, if we forget that one, we can, what we can do for dead load calculation, we can assume certain depth and we shall stop it there and we shall calculate. What we can do it here, we could do other way also, that means from D here itself we can provide our new overall depth. Maybe say 94 plus 5 is your say, so which is coming 100 plus 15, so 115. Maybe we can provide say 120 millimeter overall depth or say 125 millimeter overall depth, that also we could do. But anyway, since we have already done that one, say 155 millimeter effective depth that we have already provided, so on the basis of that let us continue in calculation. So here we have to check whether x by D is coming within the limit or not. Now let us find out the lever arm. So lever arm Z, that one equal to D 1 minus 0.416 x by D equals 155 1 minus 0.416 times 0.15, which comes as 145.328 millimeter. Area of steel, this one in the shorter direction. Let us say AST equals mu by 0.87 Fy, that is the maximum stress that is permissible. We are going up to that. So 30.69846 into 10 to the power 6 divided by 0.87415 times 145.328. So this is your area steel. Say we shall get it here 585 say square millimeter. So we can get area of steel computed, that is 585 square millimeter. Okay. So how much we shall provide then? Let us provide 10 millimeter dia bar. So a area of steel bar equals 78.5 square millimeter. So we can get this one. So spacing required equal to 1000, because we have to calculate on the basis of say 1000 millimeter per meter width times 78.5 divided by 585, which comes as 134 millimeter. Let us provide 10 torr at the rate of 134. We can provide 130 also. Let us provide 125 millimeter center to center. So this is your the reinforcement in the shorter direction that you have to provide, that 10 torr at the rate of 125 millimeter center to center. What about the in the longer side? Longer side that we have to provide, we are having moment in that direction, that is 16.372512. 16.372512, that is the moment in the longer direction. So we have to calculate the area of steel on the basis of this, but your effective depth is different. Effective depth is not same as the longer one. So what we shall do it here, area of steel in the longer direction. If this is your slab, we can find out that one side we have I can say like this, if this is your reinforcement, the longer side reinforcement will be such like this. This is your shorter side reinforcement and there is a longer side reinforcement. So if this is your longer side reinforcement, so your effective depth will be less, effective depth will be less. So what we shall get it here then, the effective depth in the longer side equal to overall depth minus cover minus 1 bar, that is 1 bar diameter, that is your 10, minus 10 by 2, even if we provide say 10, so we shall get this one. This is the difference. That means your effective depth in the longer side, that will be reduced by the bar diameter of the shorter side. So that one it comes as 145 millimeter. Okay. So, we shall get this one 145 millimeter. So, what we can do it now, again we can calculate that x by d on the basis of this. What is the value of x by d then? X by d equal to 1.2 minus root over 1.44 minus 6.6 mu by FCK BD square. So, let us find out this part separately. FCK BD square equal to 6.6 times 16.372512 into 10 to the power 6 Newton millimeter divided by 25 per meter width 1000 times 145, that is the effective depth, which comes as 0.20558. So, x by d equal to 1.2 minus root over 1.44 minus 0.20558 equals 1.2 minus 1.11 equals 0.089. So, x by d we are calculating here. So, this is obviously less than 0.48. So, we need not change any depth or anything. So, we can take that x by d this value. So, we can calculate that now lever arm. So, lever arm will be equal to d times 1 minus 0.416 x by d. So, in our case, in all the cases you will find out for slab we are using only 3 formulas. So, formula number 1, mu equal to 0.138 FCK BD square. Formula number 1, that is mu equal to 0.138 FCK BD square. So, whatever effective depth you will get it computed, on the basis of that we can provide the overall depth also, and then we can find out the effective depth provided. That is number 1. Number 2, you have to calculate that x by d. If we know mu, obviously we know mu, FCK we know, B also we know, and D already we have provided. So, that means on the basis of that we can find out the value of x by d. If we can find out x by d, then we can find out the lever arm, which is d equal to 1 minus 0.416 x by d. So, these are the 3 formulas we are using in the slab design, and we can find out that area of steel finally. So, that those 3 formulas, and now lever arm Z equal to d 1 minus 0.416 x by d, which comes as 145 1 minus not 155 145 because we are doing in the other direction, 0.416 times 0.089. So, which comes as 139.6 millimeter. One check I should say, let us find out this value, which comes as 0.416 times 0.089, which comes as a 0.9629. If you remember, this one also we can say J. If you remember that working stress method, that we used to say JD. So, this value is nothing but here, to just with the analogous to your working stress method, I can say J is nothing but 1 minus 0.416 x by d. This is the one I can say, and in other way I can write down these equations in a similar fashion, that AST equal to mu by 0.87 Fy, that is the stress, times JD. JD is nothing but lever arm also I can say. This one, or in our case let us say mu by 0.87 Fy times Z. The same thing we are talking. So, this is the stress times the lever arm. The same thing, this is the one we have used it in working stress method. The same one we can write down here also. In other way, I can say that if you are familiar with that, if you are interested to make it analogous to your working stress method, so I can write down that JD. J is nothing but this one, that way also one can write down. Okay. So, here AST equal to mu by 0.87 fyz. I think I should write down this one, similar to working stress method, so that JD, that I should write down here. So AST equal to this much, so mu equal to 16.372512 times 10 to the power 6 divided by 0.87415 times 139.6, which comes as 324.83. I think we can ignore this portion 0.83. So we are getting this much. So spacing required equal to 1000 times 78.5. I am using the 10 torr. So 78.5 divided by 324.83 comes as 241.66 millimeter. Let us provide 10 torr at the rate of 240 millimeter center to center. We can go little less also, but anyway, so which is coming as AST 327 square. It is always necessary to write down how much area of steel you are providing, because you may require later on. So that's why you always write down this. The other last time also you have written, so that you have to check it. So anyway, so this is up to this. That means we have provided the area of steel in the longitudinal side as well as in the shorter side. Now next part is your say check for deflection. So percentage of steel along LX equal to which one shall we take? We shall take that how much actually needed, how much required, not the one how much you have provided. So we are getting this one. So let me write down the needed, that is required, that please note 585 that which we have computed, that how much we require, not the one that how much we have provided. Please note that particular one. So Fs equal to 0.58 Fy time AST required divided by AST provided, which will be equal to 0.58 times 415 divided by 585 divided by 628, which comes as 224 Newton per square millimeter. So I think we don't need it, all those things estimate. Okay. Yes. So I think we can show this which we are using, that figure 4 modulation factor for tension reinforcement, and this is the formula we have to use for Fs, because that one will give you the guideline. And we have got the percentage of steel 0.3774 somewhere here, 0.3774 somewhere here we have got it, and the 224, it means along this line, So we can say it may be somewhere here, we can get it, which we can take it as, please note, I think you can see that one, that this is the one where we can find out that factor, that is 1.5, that I have taken it as 1.5. So modification factor for P equal to 0.3774% and Fs equal to 224 Newton per square millimeter. So, that we can take it and we can find out that F equal to 1.5. So, allowable L by D equal to 20 times 1.5 equals 30. There is a case here that you will find out there is one discrepancy. In one side it is written L by effective depth, that when we have told in the last one that is L by that span by effective depth, whereas in this note they have written it as span by overall depth. So, this particular one we can take it as a span by effective depth also we can take it, because the for beam other things when we have used that say basic values 20 in that clause they have mentioned is at say your 20. So, I can just read it. So, that is in your say clause 23.2.1. It reads here that basic values of span to effective depth ratios for spans up to 10 meter, cantilever 7, simply supported 20, continuous 26. Please note it is written as span to effective depth ratios. There are few things that I think it should be mentioned clearly, that this code is not writing. The other one is saying that the span to depth ratios. So, this is a little bit say confusing. Somewhere it is writing say span to depth ratios, somewhere it is writing say span to effective depth. The other part is writing say span to overall depth ratios, that they are writing. But anyway, we shall take it say to be on the safer side. We can take it say if you take effective depth, if you take overall depth, then we shall get one values. If you take effective depth, then also we shall get another value. So, in our case at least we should be satisfied with the one that it satisfied all of them. So, anyway, what is the allowable one? You are getting L by D, that one we are getting here, this particular 20 by 1.5 30, and L by D provided, let us say if I say L by D provided, there are two values we are getting. So, 4000 by 175, which is coming as very less 22.85, whereas if I say L by D (155), which is coming as 25.80. Now, let us see how much we have taken in the very beginning. Let us find out. So, we have taken say your 24. So, now what is our status then? In one case we are safe, in one case we are not safe. That is the one that where the confusion comes. So, 22.85, 25.80, that particular one here. So, we are getting two different values. So, obviously that here we have to find out. So, the thing is that to satisfy all of them in our case with that in the code itself, that means we should modify our values, and we should at least we should be safe that a conservative designer, what he will do that particular one here, that case that he will modify, will do it, but I shall stop that. I shall be we shall find out, okay, this one will be within this limit, it will be all right, that what are the values we are getting, that within that it will be all right. But a conservative designer, he will find out, okay, that he will again recalculate, he will do it. But in most of the cases we have found that 150 millimeter could be safer one, that for this case. Okay. So, the thing is that this is your the simply supported case. Now, we have to provide the your say that reinforcement, that is your that part that we have to provide the reinforcement. What we have to do, we have two parts. So, let us first summary. Overall depth (175 millimeter), clear cover 15 millimeter, reinforcement in the shorter side. How much we have got it reinforcement in the shorter side? 10 torr at the rate of 125 millimeter center to center. Reinforcement in the longer direction, so that we are getting it here 10 torr at the rate of 240 millimeter center to center. Let us find out the 3D, 3 times D, 240, that is your 3D. 3D means how much we shall get it? 3 times 145, which comes as 435. 3D means 3 times 145, which comes as 435 millimeter, or 300 millimeter, whichever is. So, we are getting that one, it is within the limit of that spacing. So, that also you have to check. I am telling you that 240 millimeter, that is the one spacing we are providing. Now, we have to check that one as per IS 456, it should not be more than 3D, 3 times the effective depth. So, in that case we are getting that one here, that 240, and 3D means here 435. So, let us see that I can show you the clause. That is spacing of bars. So, I think I missed somewhere. Yes. Anyway, we can find out effective span, all those things we have got it. So, we can find out. Splices, minimum reference slab, yes. So, we are getting the between bars. So, between bars your horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of slabs or 300 millimeter, whichever is smaller. So, here that is the restriction we have to provide. So, it should not be, that means in our case it should not be more than 300 millimeter. So, that is what we are getting it here. This is your that summary of design, and also you have to make that concrete M25 we have used, and steel Fe 415. So, at least this much it should go to the draftsman, and from here he should be able to that make the drawing. But it does not, we do not stop it here, but at least that draftsman require at least one sketch, structural sketch, design sketch, where at least your that bar reinforcement, all those things are given. Though our code gives that where is the curtailment, all those things though it mentions, and we expect the draftsman who is doing that one, at least he is a little bit literate in that technical part. So, he will be able to provide that one. But finally, the responsibility comes to the designer, that who has designed, the responsibility comes to the designer, and he will only certify whether it is correct or not. So, but at least it should be here, and then from there we can make the drawing. For that we have a detailed drawing that we can make it. So I think we shall make it in the next class, that your detailing of that we shall make it separately. That is one part. And we generally that is the, so generally the concept that one, what is the design process? The design process is that a designer will do the design, then drawings will be made. So your design calculation and your drawings, that one should be compliant each other. That means whatever in the design book, that design report, and whatever in the drawing, that should come same. That is one part. The other part here, that it does not stop it there. If the client requires or needs, that if he thinks, if he desires, he can again go for further checking, and that is called proof checking, or the other way you can call that vetting. That it should be vetted, that design and drawing, it should be vetted by a third party, third person, maybe say any academic institute like us. So something we do it like that. So that one again, what we do, we again go through the design calculation and also the drawing, and whether it is as per that your IS codes or the relevant codes or reports, whatever it is. So then only we certify, okay, this is all right, and then only it goes for your construction. This is the process. It's not the one very simple one, but it's a very, very rigorous process. Okay, I think we can stop it here. So tomorrow we shall continue with the next one. Okay, thank you.